In section 4.2, we're going to take what we learned in graphing exponential growth functions and graph very similar functions, exponential decay functions. Together, those two different types are the exponential functions. And then also we're going to use the exponential decay model to calculate depreciation, much in the same way that we use the exponential growth model to calculate compound interest. Key vocabulary here is you're going to have an exponential decay function, and the form is the same. Y is equal to b to the x minus h power plus k. The difference is that b has to be between 0 and 1. If the base of my power is equal to 1, it becomes a linear function. But when b is between 0 and 1, or a fraction that's less than 1, then what happens is as we take it to higher and higher powers, the denominator grows faster than the numerator, and hence it loses value. So that's what creates the decay. Again, if we looked at the formula we had for calculating interest, if we're having a decay, that means we're subtracting a rate. And then this item here, just like it was the growth function, the growth factor in a growth function, it's the decay factor in a decay function. Right? Type of problems we might do is deals with depreciation, so things that lose value. Most vehicles lose value when you purchase them. A new snowmobile costs $4,200. The value of the snowmobile decreases by 10% each year. Write an exponential model, and then we're going to estimate value at different times. So this is what a decay function looks like. If you remember, the growth function started flat and became vertical. The decay function begins vertical and turns flat. So they're kind of reverses of each other. And it's very, very similar to the functions that we had before with the growth functions. And the methodology for doing, for graphing these functions is identical. So I'm going to identify h and k, do an input-output table without h and k, shift by h and k. But for right now, we're starting off with a function where h is 0 and k is 0, so there's no need to shift after I'm done. I'm going to do an input-output table, and as I did with growth functions, I'm using -1, 0, and 1. 1/4 to the -1 power is 4, to the 0 power is 1, and to the first power is 1/4. 1, 2, 3, 4. So I'm going to go ahead and graph this guy. And you see he comes in relatively vertically and then leaves horizontally. Okay. Pretty straightforward and similar to what we did in the last section. Again, if I have a negative leading coefficient, that's going to have the effect of flipping things upside down. But I'm still going to pick the same inputs. 1/3 to the -1 power is 3 times -4 is -12. 1/3 to the 0 power is 1 times -4 is -4. And 1/3 to the first power is 1/3 times -4 is -4/3. So I'd be at -12. Sorry, -1, -12. I'd be at 0, -4, and I'd be at 1, -4/3. So you can see this one, again, comes in vertically, goes out horizontally. It's just flipped below the x-axis because I had a leading coefficient that was negative. Okay, we can go ahead and put decimals in here. That's still going to be the same process. -1, 0, and 1. Now, you could also say this is 3/4 to the x power. I find that actually a little easier. 3/4 to the -1 power is 4/3, times 2 is 8/3. To the 0 power is 1, times 2 is 2. To the first power is 3/4, times 2 is 3/2. So I'd be at 8/3, that's 1, 2, and 2 2/3, 0, 2, and then 1, 3/2. So you can see that we've got a a base that's approaching 1, and you see that it tends to flatten out the graph a bit. So go ahead and practice this on your own. Do problems 3, 4, 9, 10, 13, and 14, and then come back to see the function in the full form. So as I mentioned earlier, what we're going to do is identify h and k. What's being subtracted from x? Negative 1 is being subtracted from x. What's being added on to the end? Sorry, not h. K is equal to negative 3. And now I've earned the right to forget about them. Now I'm going to do an input-output table with this part of the function without h and k. 1/3 to the negative 1 power is 3 times 2 is 6. 1/3 to the 0 power is 1 times 2 is 2. And 1/3 to the first power is 1/3 times 2 is 2/3. If I graph this, I'll have negative 1, 1, 2, 3, 4, 5, 6, 0, 2, 1, 2/3. And my graph without h and k looks something like this. And now I want to add in h and k. So negative 1, that's a shift to the left of negative 1, and negative 3 for k would be a shift down in 3. So each point goes 1 to the left and down 1, 2, 3. 1 to the left and down 1, 2, 3. 1 to the left and down 1, 2, 3. And this is my new function. Okay, and again, if we want to talk about range, y is going to be greater than or equal to negative 3. Okay, similar to what we were doing with growth functions, the way you calculate the range is the same. Okay, another example. I want to identify h and k. H is equal to 4. K is equal to negative 1. Negative 1. I'm going to do an input-output table, ignoring h and k. So y is equal to 2/3 to the x power. To the negative 1 power would be 3/2. To the 0 power would be 1. To the first power would be 2/3. I'm going to go ahead and graph that. This guy's very flat. Okay, and now I want to shift it right 4 and up. Right 4 and down 1. So I'm going to take each point 1, 2, 3, 4, and down 1. 1, 2, 3, 4, and down 1. All right, let me get a blue pen, that would be more helpful. 2, 3, 4, down 1, that's the point. And then this one is 1, 2, 3, 4, and then down 1. And here's my new graph. Okay, so identify h and k, graph without h and k, shift by h and k. Same things we were doing with square root and cube root functions in the last chapter. Here's some practice for you to do. So go ahead and do go ahead and do problems 21 and 23. Come back and we'll finish up the lecture. So going back to our problem with the snowmobile, I want to go ahead and write the function. I know that I start with $4,200. I know it decreases by 10%. And they want me to write a decay model for after t years. So when I go through that, I know that my initial situation, the principal, is $4,200. That's what I spent. I know that my rate is negative 10%, negative 0.1. And my time is t. So I know that the value of my snowmobile will be equal to the principal times 1 plus the rate divided by how many times I calculate per year to the nt power. In this case, they're saying by the year, so n is going to become 1. Those will basically cancel out. So I know that my value of the snowmobile will be equal to the original cost of the snowmobile, $4,200, times 1 plus the rate to the t power. Okay, so that's going to be 4,200 times 0.9 to the t power. Okay, I went ahead and put this into a graphing calculator already. They want me to estimate the value after t years. I'd find that if I wanted to do it with a calculator, it'd be $4,200 times 0.9 to the third power. But I'm going to go ahead and read it off the graph that I have here. So I'm going to go to 3. Here's 3 years. And you can see it's $3,062. Okay, so this will be equal to $3,062 after 3 years. So it lost lost a quarter of its value. And then they want me to use the graph to estimate when the value of the snowmobile will be $2,500. So if I go back, I'm looking for $2,500. That's going to be right around in here. I'm looking for 2.5. $2.3, $2.3, let's keep going. Oh, there we go. You can see it's going to be right about 5 years. Right? There we go with 2.5, 4.9 years. So we could say that's 5 years. So at approximately 5 years. Okay, so you should have a pretty good sense of how to use the function, what gets plugged in where. Easy to read values out of a graph. Normally if I want a single value, I'd write an equation. If I want multiple values, like a couple here, it's useful to do the graph. It's also useful to use the graph to estimate values if you need to find unknowns. All right, that's the end of 4.2.